Okay, you're welcome once again. So here is a continuation of what we did in the previous lecture on matrix exponentials. So here we are going to see how you actually compute generalized eigenvectors, okay? And then from the generalized eigenvectors you can get the matrix exponential, okay? So let's start with the lemma. This lemma says that if I have x of t and y of t to be two fundamental matrices for a system, then there is a constant matrix C such that these two fundamental matrices are just constant multiple of the other. One is a constant multiple of the other if you want. And from this you can show that the matrix exponential can be written as this. Okay? Why is that? Now, we have already seen that the matrix exponential is a fundamental matrix. So suppose you have a second fundamental matrix, which is capital X of t, then by this lemma we can write e to the at as x of t times c. Okay. Now if you plug t equals 0 in here, this gives you the identity matrix. This is x of 0, which means that c can be written as x to the power negative, well, the inverse of x at 0. So you plug c back into this equation, and then you see that the matrix exponential can be written as this. So take note of this. We'll come to this. This is what is going to help us to compute this. But the question is, how do you find capital X of t? Because once you get that, you can compute this. So that's what we're going to explore in the next few slides. Okay? Now, for a fundamental matrix, the columns of the matrix are of this form: e to the at times u. If you go back to I think chapter 3, you see this. Okay, so we are going to exploit this to help us compute the fundamental matrix. From equation 1, we see that e to the at, equation 1 in the previous lecture, we showed that e to the at can be written as e to the rt, e to the a minus ri of t. So I can multiply this by u, because I know that the fundamental matrix are of this form. Multiply through by u, you get this. So that e to the at times u is equal to e to the rt. And now I can expand this, right? Using the definition of the matrix exponential, I expand this and multiply by u, and that gives me what is in the square bracket. Now know that this is an infinite series. Okay. Now if r and u is an eigenpair, if r is the eigenvalue and u is an eigenvector, right? Then of course a minus riu is equal to 0. A minus riu times this is also 0, right? We've seen this before. This is the expression we use in computing the eigenvalues and eigenvectors. So that these guys here, from here, all this will go to 0 if r and u are an eigenpair, right? This goes to 0, and then my solution is just e to the rt times u. Okay, and then we found this before. Once you have the eigenvalue and eigenvector, you know the solution is of this form, right? Now in this case, we said that u is just a regular eigenvector. Okay, but if a minus ri raised to some power k multiplied by u vanishes, okay, then now u is not just a regular eigenvector, it's now what is known as a generalized eigenvector. Okay, so in this case, a minus ri is sort of nilpotent, okay, when you restrict it to u. Okay, and we are going to use that to compute generalized eigenvectors. So a generalized eigenvector is basically if I have an n by n matrix A such that this quantity is satisfied, right? A minus ri raised to the power some integer k multiplied by some non-trivial u. If this is equal to 0, then that u is said to be a generalized eigenvector. Okay, so our regular eigenvector is actually a generalized eigenvector, but in that case k is just 1. Okay, so that is the definition for a generalized eigenvector. Now this is also important. You get this from what is known as a primary decomposition theorem in advanced linear algebra. We are not going to get into that. But if you have a characteristic polynomial of this form, where your ri's are, distinct eigenvalues, and they have multiplicities of mi, right? M1, M2, up to mk, just as numbers. All right. if you have a characteristic equation of this form, and so then for each I, right, you expect to have mi linearly independent generalized eigenvectors that are associated with the eigenvalues such that this quantity goes to 0. All right, again, this is from this theorem. So this becomes very important. Once I know my eigenvalue, I know its multiplicity. For instance, it has a multiplicity of 2, then I expect to have 2 generalized eigenvectors, and they have to satisfy this relation. So we're going to use that. So keep these two things in mind. All right. So here is a procedure for actually computing generalized eigenvectors. From the generalized eigenvectors, you get the fundamental matrix. Then from the fundamental matrix, you can compute the matrix exponential. Okay? So first compute the characteristic polynomial and look for your distinct eigenvalues. For each eigenvalue, you need to find the mi linearly independent generalized eigenvectors. Okay? If it has a multiplicity of 2, then you need to look for 2 generalized eigenvectors. Then you use the generalized eigenvectors that you have obtained, all right, to get solutions. Solutions will be of this form, all right? Okay, so this is taken from the previous equations that we looked at. Okay, so if after finding my polynomial, if the polynomial is such that a minus ri squared is 0, then all of this goes to 0, and my solution will just be of this form. Okay, so RE is an eigenvalue and U is the eigenvector, and the MIs are the multiplicities. So this is a general procedure for finding generalized eigenvectors. Okay. Now, so we're going to use an example to illustrate that. Okay, and then later on you'll see I have a 3x3 example as well in the notes, which you can take a look at. So let's compute, use generalized eigenvectors to find e to the et for this matrix. So the first thing you do is find a polynomial which is equal to this, which is this. All right, simplify this and you have this expression. This is 2 by 2, so it's easy. You can rewrite it and you have that. So you have an eigenvalue of 2, which has a multiplicity of 2. So you expect to have 2 generalized eigenvectors. So for the first eigenvector, you solve a minus ri times u equals 0. R is 2. Here is your u, let's call it u1 and u2. Compute this and you have your eigenvector as 1, 1. We have done this before, so that's easy. So a solution is given by this e to the rt, r is 2 times your eigenvector. Okay, now for a second linearly independent eigenvector, this is what you solve. You now solve a minus 2i squared times u equals 0. All right. Note that for a 2 by 2, we have a second procedure for doing that, which we have looked at. So compute this. Find the square of this, which is in this case is just 0 matrix, multiplied by your eigenvector that is equal to 0. Okay. This u1, u2 is the capital U2. I'm calling it here. So this says that any non-zero eigenvector that is linearly independent of u1, the previous one, will suffice, will be okay. So I can choose 0, 1 here, or 1, 0. All right, so I have a second generalized eigenvector. And so now my second solution is given by this. Okay, note that the second solution is u2 here multiplied by this term. Okay, you have to go back to this equation here, right? Go back to this. Okay, these terms vanish. The square term plus the other ones will go to 0. So you are left with this. That's what is giving you the solution. So your second solution is given by this. So compute what is in the square brackets, and that gives you that. So x2 is e to the 2t, t1 plus t. And so take each solution here, let it be a column of a matrix. Take the second solution to be the second column, and this resulting matrix is called a fundamental matrix. So that's a capital X. Remember that we said once you have the fundamental matrix, if you compute this, then you get your exponential, matrix exponential. So find